atomic energy, electrical energy, mechanical energy, solar energy, and chemical energy, such as is released by fire, all have one thing in common. They produce heat. Heat itself is a form of energy which, if uncontrolled, can destroy, ravage, consume. Or, if properly harnessed, heat can be made to serve man in a great number of ways. Heat energy can be converted into electrical power. Heat energy provides us with power for transportation, power for industrial progress and development. In a variety of ways, every day, heat energy is converted into useful work. Heat is motion. Heat is a form of energy. Heat is the energy of motion of the almost infinite number of molecules in any substance. These molecules, these tiny particles of matter, do not vibrate because of heat. The movement itself is heat. And because of this, heat energy can be put to work. But how is this done? How can the heat from fire, for example, be used to provide useful work? How does the conversion of the energy take place? Let us take an imaginary chain of events and link them together. First, we supply ourselves with fuel. Then we ignite the fuel. The heat from the burning fuel is transferred to some water which has been placed in a container above the fire. The molecules of the water become excited. Some escape in the form of hot, expanding gases. These gases we call steam. Now we add a container to trap the steam, a boiler. The steam is expanding, so it pushes against all surrounding surfaces, and we allow some of the steam to push its way through a tube into a cylinder. There we place a movable part, a piston, connected by a rod to a flywheel. As the steam pushes against the piston moves, turning the flywheel. Heat energy has been used to create a mechanical force, which in turn can be used to perform work. By adding valves which regulate the flow of the steam, the piston can be made to continue moving as long as there is a source of steam. This toy steam engine, even though it was made just for fun, represents the work of a great many inventors, engineers, and scientists. It is an accurate model of a piston and a cylinder type of steam engine, one of the two inventions man has made to convert the heat energy of steam into useful work. The other invention is the steam turbine. Again, we use a fuel to heat water which becomes steam. The searing hot, high-pressure steam is again allowed to escape, but this time it is forced through a turbine which we might think of as being a very complex pinwheel. Complex because each blade on the turbine wheels has been carefully shaped. The blades, or buckets as the engineers call them, are carefully designed to catch as much energy as possible from the moving steam. Mechanical energy, which turns a shaft and provides power capable of performing work. There are many steam turbines in use today. Even so, all you need to do is stand somewhere near a heat boiler to discover that heat energy is escaping in all directions. In fact, only a small part of the heat potential actually reaches the turbine. This loss has troubled engineers a great deal. In fact, it led to the asking of such questions as, why put the fire under a boiler? Why not burn the fuel inside the cylinder? Why not use an internal combustion engine? Such questions led to the development of the gasoline engine. one of the real workhorses of the past half-century. This engine, like the steam engine, is a mechanical device designed to convert heat energy into useful work. A different fuel is used, but the end result is the same. Instead of wood or coal, gasoline is used. When gasoline is allowed to become a vapor and then ignited, the increase in the pressure and volume of the gas is both immediate and great. It happens so quickly we call it an explosion. When such an explosion is caused to take place inside a gasoline engine, the result is another example of how heat is converted into useful work. If we were to look inside and see the workings of a four-stroke gasoline engine, we would see a cylinder fitted closely with a piston. Below the piston, there would be a connecting rod which would link the piston to the crankshaft. To start the engine, the crankshaft must be turned. This is usually done with an electric starter motor. If the cycle were greatly slowed down, or even stopped at times for purpose of study, we would see that as the crankshaft begins to turn, the piston is pulled down. This is known as the intake stroke, because fuel is taken into the cylinder through an intake valve. As the piston returns, it compresses the gaseous mixture of air and gasoline, and this is called the compression stroke. And the next stroke is known as the power stroke. A spark plug ignites the gas-air mixture, or in other words, starts the fire, and the chemical energy in the fuel is instantly changed into heat energy. And as a result, the piston is given a tremendous push on its way down. In a fraction of a second, the temperature of the burning gases goes up to about 4,500 degrees Fahrenheit. The pressure rises to about 600 pounds per square inch. When the piston starts back up again, an exhaust valve opens at the top of the cylinder and the hot gases escape. And so the exhaust stroke completes itself. And then the same cycle, or the same four strokes, happen again. Intake, compression, power, exhaust. And this keeps up as long as there is a fuel supply and a spark to ignite it. To provide more power and a more even flow of it, most of our four-cycle engines now have four or more of these cylinders. Such an arrangement gives at least two power strokes for every revolution of the crankshaft. And this is the most common of all heat engines. For many industrial uses, for hard and heavy work, a diesel engine is often used. Instead of igniting fuel with a spark, the way a gasoline engine does, the diesel engine compresses air to a temperature where the air itself is hot enough to ignite the fuel. A diesel engine looks very much like a gasoline engine, but instead of burning gasoline, a diesel burns oil, which is cheaper. In a diesel engine, during the intake stroke, only air is pulled into the cylinder. On the compression stroke, the piston rises and compresses the air within the cylinder to a pressure of about 500 pounds per square inch. Toward the end of the compression stroke, fuel is injected into the cylinder. Because of the high temperature of the compressed air, the fuel ignites, and the expanding gases force the piston back down for the power stroke. On the next stroke, the exhaust stroke, the piston returns, an exhaust valve opens, and the rising piston forces the combustion products out of the cylinder. Then the cycle repeats itself. Intake, compression, power, exhaust. The average thermal efficiency of a diesel is said to be about 36%, as compared with 25% for gasoline engines. But now for the very logical question. What do we mean by thermal efficiency? Well, we are speaking simply of the ability of an engine to make use of the heat energy available through its source of fuel. Most of the heat energy fed into heat engines is wasted in a hot exhaust, in cooling systems that draw off heat, and in friction, in dozens of small inefficiencies. Steam locomotives were never able to use more than 12% of the heat generated by their fuel. A modern steam turbine seldom reaches more than 30% efficiency. Jet engines, powerful as they are, sometimes do as badly as 10% at low speeds. If only there was a way of eliminating the parts of an engine that cause these wasteful losses of heat. If only heat could be directly changed into electricity. Today, in a very small way, this can be done. In these two wires, we have dissimilar metals, copper and iron. We have joined the wires simply by connecting the ends. These connections are known as junctions. Now, we cut one of the wires, the copper wire, to include in our simple circuit a meter. We place one of the wire junctions in a container of ice water. And the other junction we heat in the flame of a Bunsen burner. In so doing, we have generated an electric current. This device is called a thermocouple, and we see for ourselves that heat energy can be converted directly into electrical energy. This principle is being developed experimentally for use in man's exploration of space. This device, a SNAP 1A isotope generator, generates electricity directly from heat, just like the copper-iron circuit we saw a moment ago. But here, in this much larger unit, 277 thermocouples are designed to generate 125 watts of electricity continuously for a full year. Now let us review the purpose of our film. We have named sources of heat: atomic energy, electrical energy, mechanical energy, solar energy, and chemical energy. We have defined heat as the energy of motion of the almost infinite number of molecules in any substance. And we have shown how man has invented ways of putting heat energy to work with steam engines, internal combustion engines, and thermocouples. From these we get power for transportation, power for industrial growth and progress, power for probing space. And always the search goes on for new and better ways to convert heat energy into useful work.